Right, hell yeah. So we have statics and we got trusses, you know what I mean? So this is structural analysis, simple truss. And let's see what we got here. This is statics. This is Hibbler. You can get this PDF online. So booyah. All right, let's go back. Cool. So we're just going to kind of walk our way through, let's try to do the whole chapter, you know what I mean? Because it's kind of interesting. Because a simple truss, you really have to just pretend it's made up of individual members that are pinned together. And the crazy thing about this is a roof truss is not made that way. It's made of wood, and so if you drilled holes through wood and then shoved pins in, holy hell, they would just not be strong at all. Like, you know what I mean? They would just rip apart. Where if you have steel members that can accept pins, sure, you're good to go. But that's the only scenario where a roof truss is going to take pure compression and tension. If you do have like a wooden frame that you gusset together. So here's the idea, is that if you do have a gusset or a welded joint like this, where you got three things coming in, and welded, and maybe you have three things coming in with a pin. Just for simplicity, and I guess this is something that I would want to research, is in a lab, are these members in compression and tension only? Is there no shear forces? Is there no bending moments going on? Cool. And then the other thing is you should always be inquisitive, because we're going to have members in compression, and what happens when members are in compression? They might start to bow. And if a member bows, then that's going to, the only thing that can resist that bowing motion is a bending moment of that compressive member. Members in tension, hell no, they just get straighter. You know what I mean? So I think those are kind of the elephants in the room for like what a truss is, especially when you get to the problems and you see a truss that is just gusseted together. Okay, let's move on. All right, so you're going to run into this. Is like, what is this? Zero force members? Not yet. But a truss, has to be a triangle shape. We have a triangle here, a triangle here. If you had a square shape, it would just be, and the joints would be pinned together, it would just fall over like a stack of cards. Okay, so typically what's going to happen when we have a truss? This is probably your simplest truss. We just have three members. And again, these aren't welded joints. Like literally we're just throwing a pin through them. So you could get just three chunks of steel, drill three holes in them, and throw a pin in them. If you wanted it balanced, double up, two of them and have one in the middle or something, so you have a pin that spans, so it's kind of like a balanced setup. But yeah, you could make one of these yourself. Okay, so with a simple truss, a triangle, we're going to have to, attach it to the earth, unless it's just floating in outer space. That's kind of from the Newtonian perspective, and that's kind of useful. Like, hey, we have a chunk of mass that's rigid, and we're going to be applying forces on it. Well, we don't want it traveling in that direction, so we have to anchor it to something. And so there's going to be two ways to anchor these trusses. We'll get to that in a sec. One is a pin connection, and then this would be considered a roller or a slider, where this can only balance a upward force. This there's going to be downward forces on this truss, and so the earth can push up into this joint with just a straight up force. Now, if I took this thing and yanked it this way, this thing is just pretend like it's on an icy slope. So also when you're looking at these things, to envision the extreme possibilities, like just a slope of ice covered in melted butter, and then you're pulling on this, and it's just like, hey, that cannot take any sideways force. But this pin over here, heck yeah, you're yanking on it. You're yanking on the earth, and that can pull back. So this thing's going to be just balanced. And don't forget Newton's laws. Like if I'm applying a force in this direction, there just has to be a force in the other direction. And because there's two things going on with statics, is that you can apply a moment, and this is where it's just like I swear when people say moment, for me, I just think I don't know what I think, but reading through the text, it is a couple. So, in your playbook, anytime you see the word moment, just say couple. And then say couple of forces. Well, don't say that. But anyway, every moment can be switched with just two forces going in the opposite directions. So check this out. Let's say I did not have this. Let's say this was just kind of like a pinwheel, where this was pinned, there was no earth connection here, and we have a force on this thing. It would just spin in a circle. And then the only way to, let's just disregard. I can't go into that. We just need to move on. But anyway, so these connections are going to be our global equilibrium. And why do we have one thing that can have a pin, and a pin can have an upward force or a downward force? This can have an upward or downward force. This can only apply an upward force on the frame, or the frame can only push downward onto the earth. And that's going to be the trickiest thing, is like, hey, what's like just what I said right there. This frame can push down, the earth is going to push up. When we analyze this, we're not analyzing the earth. We're going to chop this and do a free body diagram. And so with a free body diagram, we're going to pretend like this mass is just floating, but then we're going to apply this force in this direction. And so the only place where we can resist it is this direction. So I'm going to have a 500 Newton force that way. Oh yeah, and this is where I was getting. Now, if we just pretend like this thing's floating in outer space, I put a 500 force there and a 500 force there, what's going to happen is it's going to be balanced in this direction, but it's going to rotate because that's literally a moment being applied on this rigid body. And so this is just going to tend to rotate about its center of mass. But from observation, we don't see this happening. And so we need to apply a moment or a couple or two forces that are equal and opposite. And that's very important, because if I need a force, let's see. Yeah, I need a force this way, because these two forces tend to rotate it this way. So right at this joint, I need an upward force that's going to tend to rotate it that way. Let's say I just put this upward force on. Well, now again, imagine this thing's just floating in outer space. We put this force there, this force there. It's not traveling in this direction, but it is spinning. We want to stop that spin, and so I'm going to stop that spin by applying a force here. That's going to apply a torque, and that should balance it, right? But guess what? We just applied an upward motion, so maybe it's not spinning, but now it's traveling upward. So we need to apply a downward force at this pin A. So an upward force at C, a downward force at A, and we can see that's the motion of the torque or the moment or the couple of those two forces. They're balancing these two. And we can see that the distance is the same between these. So you can really use intuition. I'm going to have a 500 here that's going to generate this torque, has to be balanced by this torque. It's going to be a 500 and a 500. And you're just like, hell yeah. Okay, so that's global equilibrium. And you need to do that every time, because you can't, like, I don't know. Like, one of the students is just like, well, I think there was some confusion. The student said, no, we want to, like, just kind of go, we're going to have a complex truss, and we want to, like, make a section and go to that member and identify what's going on at it. Now, if it's a zero force member, we can do that without global equilibrium. But everything else, we need this global equilibrium. Cool. I think, you know what I mean? But those are questions where it's just like, I'm going to throw that in the back of my mind and see if I can come up with a scenario where I don't need global equilibrium to find the forces of a truss. Unless, I think if there's some symmetry going on, so yeah, don't quote me on the fact that you have to have global equilibrium to find out what the hell's going on at one location of a truss. Yeah, so some of those things are not absolutes. Okay, hell yeah. So we're gonna yeah, so just more of this. Hey, this is our pin connection at C. It can take a horizontal and a vertical force. This one can only take a vertical force, and it has to be in this particular direction. If I just go ahead and lift it up on this frame, or pull this way on the frame, this thing's going to lift off the ground. Okay, hell yeah. So what I want to do is actually go forward, because there's going to be... So let's identify this. This is a roller. It can have an upward force. On this truss, it has to be designed so I can't just lift up on it. You know what I mean? This truss can't be having a load this way. Here's a roller here, so we're going to have these downward loads. And if we have anything going on in this direction, it's going to be balanced at A. Now, some of these things just might be balanced. Like this is the only force external, and it's downward. And this doesn't have a tendency to go that way or that way. So probably at A, there's going to be no sideways force. I'm not going to have to hold it back. Where this, look at this, I'm pulling this way. Let's just take this force and put it right down here at the roller and pull on it. Well, it looks like this joint C is going to have to resist that force. And it is. Again, it's going to resist that 450. But now we have this distance, and we generated this moment. That's a 4 feet away with a 450. And that has to be resisted by this upward force and a downward force at C to resist that moment. Now, this distance is twice, so this force only has to be half. So there's some intuition. This force is going to be 225, and this downward force is going to be 225. The sum of the forces in the y direction, or the vertical, are balanced, the horizontal are balanced, and the torques are balanced. Cool. Okay, so and hopefully these are there's going to be a section in here called zero force members, and this is where, and again, you really have to mentally put these trusses together in your mind yourself. Like, I have a pile of straight sections with holes, like metal sections with holes in them and pins, and I'm going to pin this together. And what the zero force members are going to say is, if I have a pin and there's only two members going into a joint and there's no force on that joint, then these two members don't have any force on them. They're zero force members. Now, here's the kicker that I think gets missed, especially with other people making videos on zero force members. They show you one diagram, and they show a load, maybe in a midpoint or something, and then they go through and show you all the members that are zero force. And it's misleading, because it seems like these two members are always gonna be zero force, and that's not the case. Because only if you designed this truss to only take this load right there. If that's the case, if you have do not walk, signs on this little thing over here and this little thing, and there is just weight right here, then sure, these are ridiculous. They're not helping. Maybe they're aesthetic. But if you do apply a load over here, hell yeah, we're just money. You know what I mean? And we have forces in those members. Cool. And the equilibrium says, if I have a downward force over here, then, hey, this component has to resist it, so it's going to be, pushing up on that. And now we're going to get into the next thing, because the next thing is treating these mentally. And this gets into material mechanics. All materials are springs. Like metal can be stretched to a certain point before, and you ever get a spring at the hardware store and you stretch it too much and you're just like, oh, I think I ruined it. And even the other way, you could take a spring and maybe compress it too much, and then it just gets kind of sandwiched or ruined. And so keep that in mind, that springs can only stretch so much before they... Anyway, so steel, even though when you stretch it, sometimes it doesn't visibly change length. You can change things length visibly or noticeably if you're tightening bolts. If you have kind of a long, sizable 4-inch bolt that's like being held sandwiched between like 4 inches of steel, and you just start cranking on that thing, you will physically stretch that bolt. And you can do so visibly. Like you can measure the bolt before you like crush the hell out of it, and then measure it afterwards, and you're like, dang, this 4-inch bolt stretched 1/4 of an inch. It could literally stretch about 1/2 an inch before it typically breaks for a 4-inch bolt. But materials, from their strength capacity, like the second you stretch a bolt and put a little bit of tension on it, like a 4-inch bolt, you stretch it more than 1/2 millimeter. You know what I mean? And even 1/4 or 1/10 of a millimeter, you have overstretched it. You know what I mean? So materials can only take a very small change in length before you just get into the plastic zone. Now, they'll still resist that force, but they won't resist any more force. Okay, so that was too much of a tangent, because what I want to say is that we're going to replace BC with let's replace it with a compressive spring. And we're going to say this compressive spring, so this compressive spring is this size to begin with, and we're going to jam it between B and C. And so we really have to compress it. And what's that going to do? It's going to push on this, it's going to push this way at C and push that way at B. I think enough said. And then we could also take a normal spring that's maybe just like this, you know, that's the length of it, and attach it at B and C. And we're going to have to really stretch it out. And then I think from artistic perspective, we're going to kind of double this up to show that it's like kind of a beefy spring. You know what I mean? So visually, this is the original spring, and it's hella stout. And we were able to stretch it that much, and that took a lot of effort. And so it's really going to pull in at B and C. Okay, so hell yeah. So that's going to be that in a nutshell. So back to applying a force. Back to applying a downward force at point C. This member is going to push. It can only push in this direction, but that's the upward direction. It's got a component upwards, but it also has a component that direction. But it's the component upwards that's going to balance that downward force. Cool. But then we're also, and we just explained that because this is going to act like a, and what would it act like? It would act like a really compressed spring that's just really trying to push C that way. All right, hell yeah. And when it does so, it's also pushing, it's, you know, pulling this member that way. And then so this member has to, cool. So this member is actually in tension. And we'll double it up just to show it's a stiff spring that got stretched in tension. And it's pulling back at point C. Now, so hell yeah. So that's going to be the equilibrium for that. Now what you can say, I think it's really useful to say that these trusses are made of straight members and pins. So I'm going to say, hey, this pin, and really think of this pin as like a decent chunk of metal. Like maybe it weighs 10 pounds, maybe it weighs 100 pounds. You know what I mean? It's literally like 1 foot in width, and it's solid steel. And it's all greased up, and you slide it in, and it can't take any. It's a bearing, you know what I mean? It's not as a bearing that you would think with like little balls, like ball bearings, but hell yeah, it's a pivot point for these huge structural steel members. Okay, so I think, yeah, I think that does it. You know what I mean? So these pins, just really imagine them to be just huge chunks of circular cylindrical metal. And from a Newtonian perspective, is like, damn, you gotta support those. Well, and then, but here's the thing. For a truss, it's crazy because even though, like I just said, these things could be hella metal, and these members are definitely made of steel, we're going to assume one of the assumptions, you know, for these basic truss problems is that all the weight of this truss is negligible compared to the load that we can put on it. And check it out. If I have a 1-inch steel bar that's maybe a 1 meter long. You know, I always do like 1-inch steel with 1 meter. I don't know why I combined units, but 1,000 millimeters means it can only stretch 2 millimeters before it's fully stretched. And that's when we get 58,000 PSI. And if it's a 158, we're just going to do KPI. Cool. Ooh, I really need a stylus. Holy hell. And that's KPI. So this is the pressure. And then so that means that I can put 58 kips, 58,000 pounds. Cool. In tension. And so how much would a a meter of steel that's 1 inch thick, like holy hell, like I'd pick that, maybe it weighs 20 pounds. Steel is only, this is 40 inches, and steel's about, it's more than a quarter. So this is only 10 to 15 pounds. I think it's less than 15. Could be, it's for sure less than 20 pounds. Don't quote me on that. But check it out. Something that weighs 20 pounds can support a fairly loaded semi. Not a fully loaded. With a trailer, that's going to be 80,000. But there you go. So that's the deal, is that the forces that a truss can, you can have a car driving across these members that weigh potatoes compared to the actual semis that are driving across these trusses. Okay, so that should do it. That's the assumption that these weights are negligible. Sweet, but still, think of these pins as a chunk of mass, and what that does is because there's a few ways to analyze these. One is analyze these trusses by pin. If this is pin C, and I have this downward force, I just think of the downward force on the pin itself, and you can do that because a side view, even if I have these members coming in, and I have something like this, and then I have even doubled up members over here just to make it, and then let's say I have this pin coming in. Oh, I didn't draw this very good. But let's say this pin is like oversized. And so sweet. So let's say like this member gets doubled up, and then this is a single member coming in. And then what I want to do is I want to build the road deck. In the road deck, I'm going to, make flanges, chunks of steel, and I'm going to attach them to the pin, and I want them to be nice and balanced. And so there you go. I'm going to push down on the pin, and that's typically what you would do. Well, yeah, that's a fascinating thing, because when it actually comes to building these, what you're going to do is you're going to build the road deck up here, and then you're going to actually get the weight attached to the pins themselves. You want all the weight distributed. So what you do need a bending truss, like some concrete or whatever, to actually span these pins. And I can have a car right in between, and sure, this span can take bending, but all that load is going to go right onto the pin, and this member doesn't have to take any bending. So that's another assumption that that definitely needs to be reiterated. And this right here, I have no idea. I actually, the older the bridge, the better, because you will see these pin connections, but you want to go walk up to them and actually see how the road deck is attached to the pins. Like how do they get that weight? It's very much, it's kind of fascinating. Yeah, so enough said there. But cool. But yeah, all the weight has to go through the pins, and okay, sweet. All right, so we kind of analyzed this one. Downward force. We're going to pretend that force is just on this pin. We have to have an upward force on this pin. It can only get an upward force due to this arrow, and we're just going to have a component of that, but we're also going to generate a component this way. And so that has to be balanced by this one, and then booyah. So hell yes. So now we're balanced. This is the load that we're going to put on. This component has an upward force to balance. Those two are equal. That means that this has to be bigger because it's the using trigonometry, and this is just because forces and statics teacher, this doesn't get explained, and I'm not really going to explain it, but forces obey the same kind of geometry as a triangle. So if I really can't get into it. I'll find better ways. I've done the grab a, well, I'll do it. You know what I mean? If I'm blindfolded, because this is the best one. If I'm blindfolded, I'm holding on to this ring. And in a class demo, someone, pulls 10 whatevers this way, newtons, pounds, doesn't really matter. And then perpendicular, just at that angle, let's say it's a, who cares, 3, 4, 5. And so let's say they pull 10 this way, and it's going to be a 3, 4, 5. That means that this is 8, and this component 6. So if this student's blindfolded, and someone comes in and pulls 10 pounds in this direction, and then they stop the experiment, 2 other students come in, one pulls 8 in this direction and 6 in this direction, this person can't tell the difference. It feels the same. This person is just pulling and resisting, and they can't tell any difference. And so that just shows you that forces obey geometry. You know what I mean? The length of this triangle could be 10 meters. It's not 10 pounds or newtons, but that 10 meters is equally proportional to, you know what I mean? So hell yeah. So anytime you have a force, that's 110 whatevers, newtons, you know what I mean? And you got a triangle. Make the triangle 110 meters. That'll change your life. And then I can just say this triangle, for whatever reason, is because force vectors obey, they kind of obey trigonometry. It's just a fundamental phenomenon of the universe. And so, I don't know why it has to be that way. That'd be a very good question. I think one of the other students that's watching my channel kind of asked that, and I thought so anyway, for further videos. Cool. So treat this pin as a chunk of mass. We put a downward force. We have to have an upward force from this. That generates a force that way. It's got to be balanced that way. And now this pin is not moving. Okay, hell yeah, we beat that to death. So let's, we wanted to kind of get through this chapter. So let's see what we got next. So cool. So just with these problems, hey, look at this one. I don't see a pin connection. So look at that. I don't see a roller connection on this. So it says determine the force in each member of the truss and state if the members are in tension or compression. Okay, this is fascinating because what's going to happen here is if this isn't free to roll. So here's the deal, is that let's say I have a bridge, and then I'm just going to pin it right there. I'm going to have 2 pin connections, and those pin connections are just attached to the earth. When I pull on this bridge this way, what pin is doing what? Is this pin resisting that entire load of P, or is it this pin, or is it both? Once you have to detect, because if I have a bridge or this beam, and then let's say I just cut 2 circles, and then on the earth I have cemented in 2 other flanges with holes, and what am I going to do? I'm going to take pins that are like this shape, and I'm going to slide it through that hole. So in this demo, these holes are going to be oversized. But hopefully this length, the tolerance has to be hey, this length right there, and then these are into the earth. We already concreted them in. Hopefully this length is the same. You can see that if it's not, and these holes are oversized, is if, and then I pull on this, you know what I mean? I'm not going to go through the scenarios, but you can just say, hey, if I pin these, and the pins are loose, and these holes are loose, and these two distances are different just by a little bit. When I pull on this, maybe this one has to take all that load, and this one takes none. And then sky's the limit. Maybe this one takes all the load, this one takes none. And then maybe they're perfect, where they're taking half and half, which we would hope maybe, but it could be from 0 to all, or half, and this one could be the same, 0 to all. So that would be an indeterminate structure. So, and if I have these horizontal forces, I'm going to have a balancing force this way and this way. I'm also going to have a, these forces are going to generate a moment this way, so I also have to balance that with, so if that moment is if these forces cause this whole structure to rotate this way, I have to rotate it the other way with two forces. So I at least know my horizontal, you know what I mean? So that's kind of using the intuitive method where we're not doing a whole lot with equations. We're just kind of going through and picking out the easies. All right, hell yeah. Cool, let's walk our way through. So, but yeah, see how this one has a pin connection and then a slider, roller, whatever you call it, frictionless. Okay, but here, this will drive you crazy. Because now, look at this. I have a pin connection here. There's two forces up and down. And then this one, two forces up and down. Didn't we just say that if I have these downward forces, like, was it going to be half here and half here? And this one's really tricky because we have a gusset. But you have to pretend that these gussets are pinned connections. So with a truss that's designed, even with this same structural steel, like, it looks like it's like, oh, well, I mean, I guess these are L brackets. See how you can see because they're just bolted in, they're bolted flush. Sometimes it's really difficult from the picture to see what type of steel. But hell yeah, we just have an L bracket. But yeah, we could find ways to trim off the L at the joints and then just get all the L brackets, drill holes in them, and then put a hole in all of them right at this joint right here. So this one's going to come in, and they're all going to meet at that same. So again, this is an L bracket. It's really hard to tell the L, but you could chop off the L portion right at the end, drill a hole right here, and then just attach those. But I guess this is where you would get the gusset, because just like wood, I said at the beginning, if you have this made of wood and you drill one hole in the end of the wood and then make a pin out of steel, let's say you just made it out of steel, that wood is just going to rip apart. Wood is not going to be that structurally sound. And the same thing here is I can have multiple joints, multiple, bolts, where it's not going to compromise the tension. If I do a big bolt right here, I'm not leaving too much room for that tension and compression. I'm really reducing the surface area. So that's another, observation from this gusset. But cool. But the take home, that's really this one's really difficult because it has this concept where we have two pins that have vertical and horizontal forces. Let me get some water. And then we have a gusset. The simple thing is this is a two-force member. We're going to assume that this is a pin connection. There's other of these problems. This is also, there's nothing attached here. It's just chilling in space. Sometimes it's really difficult to see where the Earth is. And then everything else just has air and space around it. And then these two forces are applied. But hell yeah, so this member can only take compression or tension. So cool. So at least it's different than the slider because we know we can at least take and maybe this book is just not. Oh no, same thing. Yeah, I was just like, holy hell. So is this one the same? Yes. Okay, so this one tripped me out because check this out. So any of these truss problems, every joint, see, it looks like this is just a big span. Like that is the mental trick. Or even right here, it looks like, well, couldn't you just make this, all the way to here? It's like, no, you have to chop that and then gusset it in, because you don't want to generate a bending moment about that member. You're just wanting this member to be in compression or tension. So that's the optical illusion on this one. This member AE is a separate member. So when I go to build this, there's member AE, there's member ED, and those two I bolt together. And you're just like, why would I do that? Wouldn't it be easier? Especially even here, DB, why wouldn't I just make a big member? Well, it's because you have these coming in, and we don't want to generate any bending moment. And so especially with trusses that are like this, it's just like, why? Like from a wood perspective, these would be 3 long pieces of wood. But from a truss perspective, I would have one piece of wood here, a bearing on the end. That's super bizarre. And then another piece here, and then I would come up like that, and then I would put a piece of wood here. So this literally can no longer take any bending. And so, and bending is in, if I have a chunk of wood in my rafter and I want to go pull down on it, well, those rafters are not meant for you to hang on even. If it's in a small cabin and you got rafters going, just like a 2x4 doing like a long 12-foot span, like, don't hang on that. It's only meant to take tension. And you know what I mean? It should look... Yeah, so there you go. So here, I can apply a load down, and this member is going to support it, and that means that this member is going to pull down on that pin, and these are going to push up. So there you go. These are going to be in compression, and they're going to apply that upward force, this downward force, and if we treat this as a pin, so let's draw this again, because this is kind of tricky, and it shows you the equal and opposite. So if I have this pin here and this, so this is not what you would do out of wood, but out of steel you would do it this way. I'm going to have a force down. That means that this pin has to have a force that way. How do we get a force that way when we have this member? Well, I'm going to take that spring and then lengthen it. So that's going to be that, this spring used to look like this, and now we lengthened it like that, and that's going to pull on those two. So it's going to pull this pin down, and it's going to pull this pin up. That thing's in tension. But the spring itself, to get it to be that shape, we pull it this way. So those are the equal and opposite. So if you wanted to draw this, and it takes some space, and we can go actually back to the section that does that. So if I have this pin here, and then this member in the middle, and the member's in tension, it's going to cause a force down on this pin, a force up on this pin, but this member itself will be pulled apart. Just like I said, this member is like a spring that used to have this normal length, and then we attached it at this point and this point, and we had to stretch it out. And I think it's useful if you're drawing like this, kind of double up, try to make this thing look a little stouter so you can visually see, like, ooh, that took some effort to do that. All right, sweet. And so now we can, yeah, so we're gonna talk about this concept in a sec, but now we can go back. I kind of like to jump around because we have this. Like, this diagram is exactly what I did. Now you can see that these, and because this doesn't do, the first time around you're like, I don't see that's even a chunk of mass. I see a speck on my screen. But this D, this is the pin. It's a 100-pound cylinder of greased steel. You know what I mean? Newton says that if we pull up on it, we must push down on it. You know what I mean? So if this arrow pushes down, this arrow is the only one that can have an upward component and balances it, but then it pulls it this way. So then we get an arrow this way, it's got to be balanced by that way. And then we see that if I'm pulling this pin this way, the only thing that can do that is a member in tension, pulling it this way. And we say that spring used to look like this, and so on the spring we have that arrow. But on the pin, hell yeah, we have that arrow. So so this is your best diagram. And if you want to go one step farther, because a diagram like this is like, hey, it looks like this is where we have that pin on the earth, so the side of a mountain, and then we have the slider right here. You know what I mean? You have that whatever thing kind of attached, and then you have the earth right here. So this one can only apply a downward force. So this structure applies a downward force into the earth. The earth actually provides the force that way. You know what I mean? So, cool. Because another way to do this is like, hey, what if you had this? What if you had this pin, and then you have, you know, some earth right here, you know, cliff, and you have one of those sliders or rollers or whatever you call them, and then you have your beam. If I did not have this cliff and this beam, what would happen to this? This whole thing would rotate that way. So the only way to keep this thing stationary and at this level is if I apply a force upward. Cool. And for this, let's say, you know, we do, since we're in trusses, this is our truss. You know what I mean? So we got our triangles. Everything is joints, nothing can take bending, and I'm going to put a downward force. So if I have a downward force, it has to be balanced by this upward force. It can also be balanced by this force. But even right here, if I have this downward force in the middle of this thing, well, yeah, it's going to be equally supported over here. So if this is a force P downward, this is going to be half P and half P that way. And then we're balanced. And we actually don't have any reaction this way. But if I come in and put another force F right here, then I need this pin to resist that force F. We just created a couple, and then so we need to balance that. If this is L divided by 2, let's say this is the length. This whole thing is length L, and this height is L divided by 2. This force generates a couple that has a moment that's F times that height, and it has to be balanced by these forces that are this distance away. Cool. Oh yeah. So we said if I didn't have these and I just had these, this would be P divided by 2, and this one would be P divided by 2. Now, those are balanced in the y direction just due to this, but the second I introduce these two forces, they generate a couple this way. They have a tendency to rotate this thing this way. I need a tendency to rotate it that way, and I need to generate that moment. And a moment is two forces that are equal and opposite. And so when we do those forces, it doesn't mess with this equilibrium in the y. It definitely adds to one of these and subtracts from the other. So if these forces are generating a moment this way, I need to generate a moment this way. So I need to increase this one and then decrease this one. And and then the distance is twice as much. So I have to increase this by just F divided by 2. And then I need to decrease this by F divided by 2. So this is pretty sweet because this is where I want to be in kind of getting some intuition. Now, there's a lot of things that I just might get wrong even for this, but at least I'm trying, and I think that was fairly decent. Okay, so hell yeah. And so why I wanted to do that is because we see that this is the force on the pin, and then it has an equal and opposite. But you can even do that one step farther at this wall. So if I say, like with this structure, the earth is pushing the structure that way. Well, that means that this structure is actually pushing the earth that way. So these are equal and opposite. And that makes sense because this thing's in compression. it's pushing this pin into the earth that direction. The earth has to balance that, and so yeah, so I guess this arrow is essentially that arrow. So maybe you don't like well, no, because even here, this component is going to be a combination of this, like of the horizontal component of this 250, and then the component of this one. So both of these are pushing the pin because we have no, both of these are pulling on the pin. Sorry about that. Holy Toledo. So both of these are intentions. They're pulling the pin in this horizontal direction. I need the earth to pull back equally. If the earth, yeah. Oh man, see, I'm bad at the equal and opposite. So I think that'll be for another day where I, I think you just do like, hey, I could just have this going on, where, yes, this pin is getting pulled away from the earth, and so I need this this joint, cemented in and attached to the earth to provide this 600 that way. And so now the earth is pulling on that pin that way, but the structure itself is pulling the earth that way. So there you go. So I could say, I could reverse these arrows, and I could say, hey, if D is being pulled in this direction, that is pulling the pin, but yeah, that pin is kind of connected to the earth, you could say, and so the earth is actually getting pulled that direction. See, I'm bad with this equal and opposite. It seemed like it didn't make sense. But hell yeah. So if I have this chunk of metal, these two are trying to pull the metal that way. This flange connected to the earth has to pull back that way. Cool. I'll get it where I can visualize an equal and opposite, but right now my mind is blanking. But this is such a cool diagram because, hell yeah, I have this pin, it's being pulled in this direction, pushed in this direction. Here's the equal and opposite forces. It's just very visually says that, hey, if this thing's in hella compression, what's that going to do? It's going to push this pin, and so that's what this arrow is. And then to get this member in compression, we're going to pull. We're going to have an arrow that way compressing that spring. So I think we're almost there. Like, hey, this pin B is getting pulled that way. I need the flange to be pulling this way. So that flange is providing a force this direction to hold. The pin is getting pulled that way. The flange is pulling that way at 600. Cool. But if the flange is pulling this way at 600, there you go. So if this is the flange and it is acting on the pin, so this is the hole for the pin, and it can provide a force this way. The only way it can do that, to provide this 600 force this way, is see, I almost had it. It's like if the I don't want to pause, but yeah, there's an equal and opposite. I don't know why that's so. If you see it, cool. But yeah, just saying it is just like the flange is pulling this pin this way. The flange is connected to the earth. So this flange is pulling the earth. Yeah, there you go. So there, yeah, it was this arrow. So yes, the flange is pulling on this structure this direction, but then to throw this equal arrow, sometimes you need to leapfrog it in front to be like the structure itself is pulling on that flange. Oh man, I'm sorry. This is. I don't know why I go blank when it comes to equal and opposite. I thought I was doing pretty good where you have like, hey, you're pulling on the earth, and the earth is pulling back. So yeah, there you go. So I wanna pull this flange this way. The earth has to grip into this flange with those connections with the rebar and the concrete, and the earth is pulling back. Yeah, I don't know. So what arrow does this represent? Does this represent the flange pulling or the earth pulling or both? I don't know. So, damn it. We need to move on. We tried our best, though. But hell yeah, this diagram really shows you the force on the pin. Look at that. The pin's getting pushed that way. Why? Is because we have this in compression. But these are the arrows on the spring that shows compression. The spring is in the members. Cool. All right, so zero member forces. Now again, these are joints where we don't have a force being applied. If there's no force being applied to this joint, then let's see. Yeah, and it's because that if you put a coordinate system, if I put a like let's say, well, like if this is joint B, can't I have a downward force? Well, no, because if this is the coordinate system in the YX, only this can balance. Only this has the ability to have a vertical component. But if it did have a vertical component, it would also have a component that way. And this member can't resist a component that way. So again, you have to pretend that these things, and they are literally chunks of metal with holes in them that are able to freely, kind of collapse. Even though they're in a stable structure, still have that in mind that they, that's the idea. They can't take moments. They can't. So yeah, the one that's visibly just kind of wild. See, I even kind of drew it wrong. Like this would be a member. And this would be a member. So if I have this in a truss, and then I have these two members, and then I have this. If I pull down on this joint, these two can't do anything. These two are not helping. These two can just be in compression or tension. Only this joint can pull up. Cool. So over here, here's the coordinate system. If I have a downward force at this would have to have an upward force. We would have an over force, and this cannot provide this force that way. So therefore, this member just can't have any compression or tension. It can't have that. Cool. Whoa. All right, sweet. So, now, why isn't this a zero force member? Well, let's pick it apart. Let's say I do have, and maybe it is. I don't know, but I do have if I have a downward force here, I'm going to have this to have an upward component. So this one's going to have an upward component. That means that this is the force, and then I'm going to have an over component. This one can support that. So we're good to go on that one. That's not a zero force member. So it's almost like easier to pick what's not a zero force member. And maybe I totally mess this up. So for this diagram, what was it even saying? Yeah, let's pick through some of these. So right here at joint A. So they did joint A, and this was for joint D. Yeah, we already did that. So joint A, same thing. If I had, so they're saying if I have a upward force, just pretend you have this is in tension and it's pulling this joint A. This can only have a component this way or this way. It can't do anything about that upward or downward. So therefore it doesn't exist. It can't have a force in it. The only contingency that a lot of the people on this topic don't talk about, and it explicitly says, if I put a force here, hey, I'm good to go. This is not a zero force member, because let's check it out. this can balance, and so we're just check on reality. Hey, this is still going to be 0. Okay, let's do another one. Let's take a force at a 45 on pin A, and are we still good to go? This is going to have a component upward to balance this component downward, and then this for sure has a component that way. Yeah, this will balance that component that way, so we're good to go. So there you go. So I can have as long as this force at A, as long as there is a force at this pin where you have two members coming together. So that's the definition of the zero force member. One of them is where if you have any two members coming together at a single pin and there is no force on them, then for sure those are the easiest to pick off. I mean, it's like you didn't even need it anyway. But like we said, it's like, hey, maybe at some point you're going to generate a force there. And these things can take forces, and they can literally take a force at any angle. So that's the other thing. If you identify a zero force member, always be thinking that this load might be applied in different ways and at different sections. Cool. So, all right, so this one, which one are we observing? So now we're observing this one. This is where we have three members coming together. And again, this member DC is its own individual member, and this ED is its own individual member. And what we're going to say is that if this thing is in tension, that's kind of what they're just assuming that this one's in tension. Well, it can't be, because these would have to resist that tension, and they just don't have any component in that direction. So therefore, this is a zero force member, 0. All right, so here, let's see. Oh, so here maybe this is interesting. No, what the hell is he saying? I don't know. Oh, they were saying point C. I don't know what they're talking about with this diagram. ABE. ABE. Oh, therefore, if both of these are zero force members, you could have just built this truss like this. But the video that I watched on the YouTuber that's doing pretty well is saying, like, that's the other thing with these trusses. Like, if I have a force this way, this one. Well, no, this one's going to be this one should be in tension. This member should be in tension. But with a truss, your top members sometimes are in compression. So just imagine if this thing was in compression and it was made out of a long chunk of wood. This would be in compression. What happens is that this long piece... Oh, never mind. What they're saying is that if these are zero force members, why include them? But if this force was going the other direction, and this member was in hella compression, it's really long. It's going to bow. From a material mechanics perspective, it's going to bow. And so just having, something secure it in location keeps it from bowing. But then, you know what I mean? That's crazy, because if this member is one long piece and it begins to bow, you are going to generate force in these zero force members. So that's what drives me crazy, is like the ideal compared to, but that's, this is drawn horribly wrong, because we should say that this is still three members. We still have this member pinned to this member, pinned to this member. And the only thing this thing can do is take tension. Yeah, it would be fascinating. I'm going to try to come up with one of these where you have zero force members and this force is the other direction. Well, I think we just did this. So this will blow my mind if, like, hey, you change this force in this direction. Oh, this is wickedly unstable. You know what I mean? Where you would for sure just want to do this type of thing and pin it. And now, okay, heck yeah, this member can take compression. Because that's the other thing. From a material mechanics perspective, you have a long member, and then you see compression, holy Toledo, just think bending. You know what I mean? Anytime you drive by the countryside and you see someone build their deck hella high with 4x4s, you're just like, holy Toledo, it's like Bambi. You know, just like, who the hell designed that deck? I mean, it's just like, you could, and just even 6x6s or 8x8s would have looked way cooler. And, you know what I mean? Yeah, some things in life you're just like, you just look at and you're just like, well, why'd you build it so sketchy? Yeah, you don't even need to know anything about anything. You can just be like, that looks sketchy. All right, so hell yeah. So, yeah. But if this is pulling this way, I would just imagine these are in tension. And it wouldn't matter if these were 3 links. Oh, I really need a stylus. I'm gonna get worse joint pain just using this. It's not. I'm not even using a mouse. It's just like the touch little pad on a laptop. Oh man. All right, so we need to move on. But hell yeah, we're doing pretty good. Kind of driving through this stuff. Just kind of the stuff that you might get hung up on. All right, hell yeah. So now we will go to that one problem. You know, because this is the stuff that's just like, well, why this pin can take 2 forces, this direction and this direction. Well, so this is where you got to talk about this 2-force members. So member AE, I can only apply a force this way or that way on member AE. And that's the other thing, is you really have to imagine that this member is separate. It's not a long member from D to A. If that was the case, it would be an indeterminate structure, I think. More water. But because this thing can either be hella crunched and providing a compression force or stretched out and providing a tension force at A, those are the only 2 things that that can do. And so then we can just redraw this thing. Ooh, that was really bad. But the external reaction is just going to be that. So it's like, here's a better idea. It's like taking that little, and I'll do a roller. So it's like, ooh, these are going to be really hard to draw. But it's like taking a roller support, putting it right here, putting some earth right here, and then attaching it to point E. So those are synonymous. So this is kind of like the hardest part about this chapter, to identify that and just not get spooked out. But actually, I swear, the hardest part is to identify that this is its own separate member, and it's not just a continuation member all the way from A to D. All right, sweet. So we're going to take a look at a few of those. Because this one, like we said, this is a gusset, but this is acting like a pin. This can only take a tension or compression along this. So if this can only take a tension or compression, we can sum the moments. So yeah, if this, let's just say it's this way, this one is going to be up, and let's say this one's going to be that way. So there's our forces. I'm going to sum the moments right here, and when I do that, I know this, know that, and so this is the only unknown. Cool. I could have also summed the moments right here, because this force goes through that point, and then this was the only unknown. And then once I know either one of, let's say I know this one first, then some of the forces in this direction, I can get this one. It's the only force in that direction. And hell yeah. And even before that, sometimes it's kind of interesting where you're just like, oh, if this is the force up, this is the force over, and this is the force over. Yes, I don't know these 2 yet, but I can just use the sum of the moments in the y. I can always get this one. It doesn't help me get these horizontal ones. I need the moment equation either there or there like we did, but order of operations, sometimes it's just nice to identify one force and then have that number on the board, even if it's not useful for the next equations. Okay, sweet. I Well, I'm glad I'm doing this just because I didn't want to do any videos tonight. And yeah, so yeah, this is cool. So again, there's that roller support, 2 forces. And then I'm sure they want to pick 0 force. So let's pretend that this force doesn't exist and this force is right here. Well, you didn't even, these are 0 force members. You didn't even, this is just extra. You didn't even need to design it like that. You could have just designed it like this, and then you're set. Even up here, if I'm not applying any force right here, then this stuff's redundant. There is no force in these members, and they're not doing anything. But maybe at some point you do want to apply 2 forces, or 1, or whatever force at that pin. So yeah, it'd be kind of fascinating to see this in real life, to see like, oh, look at that truss, and it looks like there's no force ever going to be put on that point, but maybe in some sort of situation they are, and it wasn't an unnecessary piece of the puzzle. But this really isn't helping anything else. It's just another thing just attached to the same points. It's not helping this member any of the members be in compression, balanced like that. Okay, moving on. All right, this one looks interesting. Hell yeah. Yeah, and just get more complex. I want to talk about that one on a different day. These are the ones where it's just like, yeah, globally. So look at this. Maybe we can talk our way through it, because I have I'm going to have probably an upward force there and maybe an upward force here. I'm going to have a pushing force that way, so maybe this has to resist. And maybe this has to also push because it's getting pushed. I just don't know these 2 values. And so what I want to do, I don't even know. Yeah, this might be kind of tricky. Yeah, so this is one where you need to like separate into 2 equations for global equilibrium, where I'm going to have this, and I'm just going to say an upward force on this one, and let's say on this one, and I'm going to include this force onto this diagram. But when I do this one over here, I'm going to have a opposite, and I'm going to have a downward force, and I'm going to have no P right there. So that is kind of the trickiness. But so now we can solve for, we could probably solve for, yeah, I don't know. If I sum the moments here, I'm going to have 2 components, this component and that component. But if I came over here, I'm not going to have that load P. And if I summed, I might be saying wrong things. No, I'm not. If I sum the moments about there, I would still have those 2 components that I don't know. Yeah, this one is tricky. Huh, yeah. All right, so for another day, these are the ones that I like. I don't know why I can't just, obviously I couldn't intuit it just right off the bat, so that's my limit. Alright, so we haven't talked about sections yet. So this is the method of sections. And so this is what I'm kind of pretty good at. So, oh yeah, and then this one do you need global equilibrium? I guess not. And so that's kind of wild. So yes, this is true, because I could find global equilibrium over here and find the reactions. Let's say the reactions are like that. But check this out. If I come through and section this, I can just pretend like this thing is its own experiment and do a free body diagram. As in, totally neglect this. Build this thing where we have 2 joints just kind of hanging out. And you're going to float this thing in space. I like to think of like making little rocket boosters. where you apply a rocket booster here, or just a rocket, and it applies this force in that direction. So it really wants to get this thing going that direction, and I need to balance it. So right here, this can only be pulled this way or pushed that way. This can only be pushed or pulled. So this is the only thing that has a component in the, and then this thing. So this member is the only thing that has a vertical component and a horizontal component. So this vertical component has to balance that. And once this is 1,000, then you can find using trigonometry the value of this. And that value will have a component that way. And but enough said. Let's say you just wanted to find the that member right there. You did it. You sectioned it and you found that member because it's the only member that has an upward component to balance that. All right, hell yeah. So moving on, and let's try to do some more of these because they do pretty good examples. Now you could have done the other thing where you sectioned it this way and you pretend like this is the only thing in the universe. Well, now you do need to know these forces. You need to know that one and then the two right here. And then what you would do is, so if you wanted to find this, it's the only one with a vertical component, and you're going to find that vertical component is going to be equal to that reaction. So cool. So I guess this reaction just in general is this 1,000, and we could have saw that from global equilibrium. If this is up, this can only take an over, and this can maybe take it that way, so this has to equal that. All right, hell yeah. I think there's one more way to solve this one, and it's also, so this is also kind of wild. So we're going to take this same cut. So same cut, but we're going to find a different force. And so this one's going to have we're just going to assume that these are in tension, and then this one's going to be in tension. Look at these two arrows. They approach this. So even though we cut this out of reality and we have this floating in outer space, we got our little rocket booster going this direction, applying this force. But I just want to know this one. So how do I do that? No, I'm sorry. I just want to know this one. Sorry about that. It's because I can see that these two forces meet at this point. Even though I did a free body diagram of just this section, and this point is no longer even on that rigid body. What I like to think of is just extend a chunk of foam out here and connect it to the rigid body that's just massless. And I don't know, it's just kind of the definition of summing moments about any point. It can be any point in the universe. It's kind of a fascinating concept. But hell yes, we're going to sum the moments about C. These two forces go through C. This is the only one that's generating a moment about C that we don't know. This is generating a moment about C, and we know that's 1,004 meters. So it's got to be balanced by this force that is 2 meters. So hell yeah, so we just know this force got to be 2,000. So there you go. So there's some intuition where it's just it seems like you need a hell of a lot of algebra and trigonometry. But some of these you can pull off intuition, especially getting more intuitive with moments. Being yes, this is generating a moment about point C of 4,000 Newton meters. And then this will generate a moment about point C. It only has half the leverage arm, so it has to be twice as big. I think my finger's about ready to fall off. So, but I think we almost covered everything we wanted to cover. There's just one more thing about sections that's kind of unique, because those are the two things, and there's one more. If you have this, so there's two ways to look at this. I'm going to section this out, and I'm going to redo that. Try to get as big a section as possible. So I just have this. I'm going to have a force that way, positive force this way, and a positive force that way. I do have 1,000 on here, and what am I going to do on this one? I'm going to say that I don't even know. What do they do on this one? I think they actually find this force first. So once they find this force is 3,000, then they know that this force is balanced. And then they'll, yeah, is it, man, I guess because you can cut one of these where it's just a zero force member. So maybe we should go to that one first. Oh, we're going the wrong direction. No, that's going to be the whole deal. Oh, yeah, but if you did sections and you cut this section out, okay, this one's going to have a vertical component, and these just have horizontals, so therefore I know this. So this is my section that I cut out, and now I know this because some of the force is in the y. So the trick on this is to cut a section where maybe you can just use one equation, and that's going to be sum of forces in the y. Oh, that's a horrible summation sign. And then you can do it in reverse. So let's say I section this out, and I say this is the only thing in the universe, and this thing's gone. But I would have to use global equilibrium. So this was 600. I would have a 600 here. So keep that in mind. And then I would have whatever reactions here and here. Hopefully I got those right. Nope. This, yeah. This would be that way. This would be that way. And then so if I had this thing going on, I would have this force popping out, and I would have this force popping out of this chunk of metal, and then I would have this force popping out. And I would want to sum the forces still in the y direction. I know this one, and this is the only force in the y direction. So that shows that even using sections, you can always do it either way. So let's go back then. Yeah, or just do this one. So we're going to do this one in two different ways. So why would we section through here? Well, let's do that. So I'm going to section through here. And then which section do you want to use? Do you want to use this thing? Or do you want to use, and you have to use that thing. So yes, that's the intention, because this arrow goes towards B, this arrow goes towards B, and now you can see that all these arrows, you're just assuming these are in tension, go, and it doesn't matter, they could be going in compression, but they have a line of action through B. But this arrow is the only one that doesn't. So I can sum the moments about B of this chunk of metal. So this is the free body diagram of this thing. We're excluding this thing from our analysis, and we're summing the moments about B. This is the only unknown force, and so we have to include this one, this one, this one, and this one. But this is the only unknown force. We want to know its perpendicular distance. That's the only hard thing about the trigonometry, but we can solve for that. Okay, so now how would we solve? So what we did was we just solved for that force using that cut. Could we take a different cut and solve for this force? Well, what I would do is do this right there. So now these two forces go towards point B, and then this force goes that direction. So it's actually a simpler way to do it. I'm going to sum the moments about point B, and this is the only force. And I still have to include this. Like, this is the chunk of metal that I'm analyzing with a free body diagram. Floating in this in outer space, applying this force, applying that force, and we know that it's not traveling in the vertical, horizontal, or spinning. And if I sum the moments about any point in the universe, it can be outside the rigid body. It's kind of wild. And because these two forces go through that point, this is the only force that's unknown that has a component that's affecting the moment. So this moment of this force has to be balanced by that force down, and the moment of that one, so that's going to be a that way. This one's going to be a that way, so who knows? This one's 2,000, this one's 1,000. Oh, no. So this is generating a 2,000 and a bigger lever arm, so that's going to be like a 4. And then this one's going to be 2,000, and this one's going to generate a 2. Oh, this is 4. No, this is going to be an 8. So this is going to generate an 8 Pascal, 8 kilopascals. You know what I mean? 8,000 Newton meters. So this is 2,000, This is 4 meters. That's the leverage arm of this. So we get but just in general, we get an 8 up, and then this has a down of 2. So we're going to have a 6,000 pascals or Newton meter torque. That has to be balanced by this. Let's just guess. You know, what the hell is this distance right there? It looks about 2. So I'm just going to say that if this is 2, this has to be 3,000. So there you go. So this force would have to be 3,000. And I bet you that's the case. You know, I mean, sometimes the geometry just kind of works out, and they say this force is 3,000. I kind of remembered that. But there you go. So just kind of using some intuition to kick those out. So they sectioned, again, they sectioned this. Oh, my finger's ready to fall off. They sectioned this, did a free body diagram about that, have all these forces approach point B. This is the only one that doesn't. So there you go. You're going to sum this moment, and I guess that distance is just 2 meters. Imagine that. Cool. Yeah, and this, you know, because we section, and the sections are different. See, we sectioned right there. So you're not taking the same section because all those forces are going in bizarro directions. And you know, if I sum the moments at point E, I have 2 unknowns. You know what I mean? So right here, these two converge at point B, and it leaves 1 force, and that's the force in that member. Hell yeah. Okay, so what are they getting at this one? I swear they did AA first, found that this was 3,000, and so let's do that. So I think, because some of these you can't solve just with one equation. So if I section this, because if this is 1,000 down, I don't know if this is just balancing it and these are 0. You know, I don't know if these are 0, but we found that this is 3,000. So if this is 3,000, this has to be 3,000 as well. Let's say this is 3,000 in tension. This has to be 3,000 in tension because this can't take any horizontal force. And so if those balance, therefore this has to be 1,000. So so I guess you could solve for this one not knowing anything. Because you would say if there is a force in this direction, you would say the component, so you would say sum of the forces in the x direction is going to be, is this component in the x, which has the same ratio as this component in the x. So whatever this one, whatever force this member has to equal that member. And if, oh, no, never mind. Yeah, scratch what I just said. Yes, if this is 3,000 that way and 3,000 that way, we do get a downward component, and that's additive. Whatever this is, we're going to have this 1,000 plus that component downward, and this component has to resist that. Has to be in hella compression to push up on that pin, and so I'm glad we're using our intuition there. So hell yeah. So this member, so from intuition, this member BE has to be more than 1,000. Well, depending if this is in tension. If this is in tension, this is going to be more than 1,000. Let's check out what it is. So member BE, this is force BE, is 2,000. No. Yeah, force EB or force BE is 2,000. So there you go. So glad we didn't royally mess that one up. But there's one where you could solve for a 0 force member using sections. So like right here, let's say I know that this one's in tension and this one's in tension. I'm going to cut right through here, and then I'm going to have the arrow down and just sum of the forces in the y direction. Like this one can't balance any, so therefore this is a 0 force. So that you're still finding that using sections, and I can section it, you know, the opposite way, where it just makes your jobs harder. Where, okay, so right here I'm going to have a downward arrow, an arrow to, I'm just going to assume they're all in tension, and now I'm going to sum the forces in the y direction. And so these don't have any, these are unknown, don't know it, don't know it, don't know it. This is the only unknown. And so some of the forces in the y direction, I've done global equilibrium. I know that one, and know that one. And so up, down, up, you know what I mean? And this has to be equaling out. So there you go. We used sections to find, oh, holy hell. But, okay, if we did that, these would totally have to balance. That's wild. This still has to be 0 because of its geometry. So that's kind of cool. It's kind of cool that you can use global equilibrium. You know what I mean? You can find this value and this value using global equilibrium, given your input forces. And then you can do a crazy big section on this where you sum the force, and you just assume this is positive tension. Sum the forces in the y direction. These all will balance. So these are the forces in the y direction. These will perfectly balance out. So let's check this out. So AY and DY must add up to 1200. And is that the case? We have AY, and then where's DY? Yeah, it should be. DY is 900. So there you go. AY and DY add up to 1200. All right, so hell yeah, this video is hella cool for me. I mean, it's not the fast as approach, but we learn a lot. And I think I'm about done because I think I got through. And like I said, my finger's ready to fall off. Cool. And then there's just really hard problems. So we'll go right to the end. And you can do 3-dimensional trusses. I have not looked at that, so that is completely unknown to me. But sweet. So like right here, this is a 0 truss because it can't have an upward load, downward load. These two members can't take that load. But if I have a force here, then this becomes a non-zero truss. You know, so as you move the weight across this one, like once the load gets to here, this is not a 0 force member. But if the load's anywhere on these other pins, this is a 0 force member. And some of these don't have 0 force members because or just don't have obvious ones because you don't have just two things chilling out. Yeah, so here, this is a 0 force member, and this is a 0 force member from that same idea. And even if you have one at an angle, let's try to find one of those, and that would be a good place to end. Do a 0 force member where like the truss is at an angle. Yeah, right here. So if I have this member right here and I section this out, because this involves rotating your axes. Okay, so that's the section. I know this one, I'm just going to assume is in tension, and then it's going to be balanced by that tension. I'm going to say that this is my x prime, so it's a rotated axis. I'm going to draw in the y prime. So this is the y prime. This component, if I do have a tension along that component, is going to have a component in the y prime direction. But these do not have any component in that rotated direction. Therefore, this member has to be 0. And you don't need to rotate it. You know what I mean? You could use trigonometry to say, look at this. This has, if this is in tension, it has a geometric, this is the vector, and here's its geometric components. This component is going to balance that component. What were we saying? Oh yeah. So these components have to balance. I'm doing it in reverse. These components have to balance. If this component's hella bigger, this one has to be hella bigger. It can't be smaller. So if that horizontal component is smaller and this one's bigger and this triangle is bigger, well, now you have an unbalanced force. This thing's going to be a dynamics problem. So there you go. So that's showing, even just using the XY coordinate system. Where if, because the thing is if I have a force here, then, this one can't just get bigger. Because if this one gets bigger, this one has to get the same size and balance out. And so that's two different ways to show that this is a zero force member, but I think the easiest is to rotate your coordinate system and say, oh, yeah, these are in this new coordinate system. You can just call it x and y. You don't have to call it prime. And if I had any force this direction, it would have to be balanced by one of these two members, and they don't have a component in that direction. So therefore, this member is a zero force member. And we're done. So thanks for joining me on this one. This was pretty sweet. Yeah, I feel pretty solid on this stuff. Okay, hell yeah.